The Horizon 2020 project plan for us is dedicated to the strategic assessment of the whole European energy system for the next decades. One of its objectives is to develop tools that help solving the problem of determining the optimal generation mix with the optimal transmission and distribution grid capacities for a given long-term horizon. This model is divided in 3 layers. The lower layer is the unit commitment problem, which is a hard mixed integer nonlinear optimization problem regarding the short-term scheduling of electrical generators. The middle layer concerns the mid-term management of energy reservoirs in the face of several uncertainties, such as climate, demand, outages. It consists in evaluating an approximation of the expected operational cost for a given installed capacity under the assumption of a meta-scenario. The higher layer regards the evolution of the energy system, which includes, for instance, the construction and the commissioning of generators and energy lines and investments in different generation technologies. To solve this complex optimization problem, we are developing SMS++, the structure modeling system, which aims at facilitating the implementation of general and flexible algorithms for optimization problems with several nested layers of structure. The main component of SMS++ is a block, which represents a block in a block structure mathematical model. A block contains an objective and any numbers of variables, constraints, and subblocks. A block may have 2 types of representations. The abstract representation is formed by its objective and a list of variables and constraints. The physical representation is any data structure that describes an instance of that block. For the capacitated facility location problem, for instance, the physical representation would be defined by the sets of customers and locations, opening and transportation costs, and demand. To solve the model represented by a block, SMS++ provides a unified solver interface, wrappers for existing solvers and native ones. Besides many other features, solvers can react to changes in a block, aiming at re-optimization. And SMS++ offers native parallel capabilities for solving a problem. The midterm problem in the Plan for Us project is a multistage stochastic optimization problem, which presents a UC problem at each stage. A desirable feature is that the representation of uncertainty does not require any adaptations of the existing blocks, so that any implementation of a block that's part of the deterministic model can also be part of a stochastic model. A fundamental task in the solution process of this type of problem involves the simulation of random variables and updating the data of the UC block according to a given realization of the random variables. Updating specific parts of a block, which are affected by the random variables, can be done via its abstract representation or, in a more user-friendly manner, via its physical representation, simply by knowing the names of appropriate methods. A data mapping is defined for identifying the random variables of a block and offering a mechanism to update the realization of the random variables of a block. Finally, we have the stochastic block, a block that's able to turn any block into one representing a stochastic model. It has a subblock, which is becoming a stochastic one, a data mapping that identifies the random data of the block, and a probability distribution or stochastic process characterizing the random variables. The midterm problem is represented by an SDDP block, which is composed of a set of stochastic blocks, each one associated with a UC problem. SMS++ provides a powerful and flexible interface to exploit several specialized solution methods together in parallel, which is crucial for solving these huge-scale, highly structured problems.